fun. Okay, so I'm going to tell you something about a kind of mathematics that you probably don't see around here very much. It's kind of mathematical logic. So I'm going to show you lots of scary symbols from mathematical logic, not because I want you to understand them, because I want you to see that they exist and kind of get an idea that there's some stuff out there that it might be fun to go and find out something about. Okay, so scary symbols just to kind of tantalize you a bit, but not very many of them, don't worry. Some pretty pictures as well. So, okay, so distributed systems are what computer scientists is the name, the description that computer scientists use to describe the underlying infrastructure that drives everything you use. Right? All the great big systems that drive the big databases that you get looked up in all the time, all the stuff that drives all the server farms in the cloud and stuff like that. It's distributed systems is the underlying conceptual model for that. And now, because they underlie everything and they're everywhere, that means they have to talk to one another, and that means there have to be interfaces between them, and what the interfaces between systems are the places where everything goes wrong. Right, that's where all the failures are, really. Now, in recent years, there's been a lot of massive progress using ideas from logic to support program verification, and people down the road in Facebook and in Google and stuff now routinely use advanced ideas from mathematical logic, some of which are based on some of the stuff I'm going to tell you about, to prove the correctness of programs, to find bugs in programs, and actually make stuff a lot better. Now, what we need to do next, particularly in the context of the kind of stuff that the Institute is interested in, is take some of that technology and make it tell us how to make the interfaces between all these great big systems that we rely on better, more reliable, break less often. Right? So that's kind of where we are. Okay, so what are the basic ideas in distributed systems? Well, as a if you take a big book on distributed systems and read it, and and just reflect on it a little bit, what you'll kind of abstract from that are that there are some key concepts in there that you have to handle. And the first is perhaps the idea of location. Hasiba is going to recognize some of this because she thinks about these things a bit. So what's going on is that whenever you have a great big system which is scattered all around, all over the place, there are different places, and that those different places, which are connected together, there are the resources that the system must manipulate. Right, they might be the people who are running the system. They might be files. They might be bits of databases, or they might be the amount of money in a bank account, and somebody might want to transfer some resource from their bank account to somebody else's bank account in order to obtain access to some product or service. And all of those things are about moving resources around between locations. And the things that do that are the processors that describe the dynamics of how that happens. How do I transfer this money from this account to this account in such a way that somebody can use it to buy something? Right now, we can actually describe all that stuff very precisely, mathematically, and reason about it logically. And what we need to do to make all this stuff work, so that next time you try to make a payment to a bank that you haven't made a payment to before, and you get the account number a little bit wrong, something tells you that you got the account number a little bit wrong and stops the thing happening, instead of just disappearing your money to the Russian mafia or whatever. So what has to happen is we have to find a good way of modeling all this stuff mathematically in such a way that we can use it to make things work better. And that is in the spirit of program verification that has been massively successful using this kind of technology. That's the thing to remember. There's a track record there now of this stuff really working, but it's not really working yet at the big system scale. And that's the step we need to take. Okay? Hence, of interest to the Alan Turing Institute, I hope. So, when we think of a system, we have this idea of location, resource, and process, and that's describing how it's doing its stuff. Typically, always also, we need to think of the system as being situated in its environment. Now, when we think of a particular system, we want to conceptualize a system, but when we conceptualize a system, we kind of draw a boundary around it. We think this is the thing we care about. So it's your bank's databases or something, not somebody else's bank's databases, your bank's databases. So from the point of view of your bank's databases, all the other bank's databases are just throwing things at your databases in a kind of apparently random way. Right? So from the point of view of thinking about it mathematically, you've got the system you care about, and you've got other stuff, and other stuff throws stuff at the bit you care about. So we treat that as an environment, and we don't model it in any kind of structural detail when we think about this. We'll probably just model it as some kind of probability distribution or something. Okay. So, on the other hand, because there are all these big systems talking to one another all the time, we need to be able, in order to understand how all that works in aggregate, we need to be able to understand how one model fits together with another model, fits together with another model, and so on. So we really do need to think about how to compose models of one system with models of another system, so that they, when we put them together, that composition captures the communication that's supposed to happen between those two things, right? Because it's when things try to communicate with each other that stuff goes wrong, because they get the protocols wrong, they get the language wrong, it doesn't quite work. The assumptions that this one was expecting aren't quite supported by this one, and something goes wrong. So that we have to get all of that right, and that's why we need to do this kind of mathematical modelling. Okay, so how do we go about doing this mathematically? Well, we've identified these key components: location, resource, process, environment. Now, mathematically, there are all natural ways of capturing all of these things. So the trick, what we want to do is to find, for modelling these great big important distributed systems, we want to find the natural mathematical way for talking about all these things, and then find natural ways of fitting them together so that we get a good story about how things work. What we don't want to do, and this has been proposed previously but is problematic, is to have some kind of glorious universal language that can describe all of these things. And that's actually, we can certainly do that, formally, no problem at all, but when you do that, because it's a universal language that's not ideal for any of these things, it's not great at doing any of them either. And you end up doing a lot of coding that's unnecessary, that's irrelevant to the task you really wanted to solve, just in order to say that I've got a process or a resource or a location. And you don't want to have to do that. What you want to have to do is describe these things in the most natural ways, and then find natural ways of putting them together. So that's already telling us that we're moving slightly away from the way in which computer science and logic and stuff has tended to treat systems previously. It's tended to treat them as things that you just need to find a uniform, universal language to describing. But we're moving towards the more traditional mathematical modelling approach of the kind that an engineer would use when building a bridge, right? In which you just find the right thing and make it fit together with the other things that are the right things. You know? So you find a good model of the stresses on the bridge, in the struts on the bridge, but you also find a good model of the way the concrete behaves, and then you have to find a way of fitting those things together. So it's a mixture of the ideas from civil engineering and mechanical engineering and probably electrical engineering. These are just to get a good description of how a bridge works. Right? So it's the same kind of philosophy as that. Okay. So I'm going to show you a couple of slides now, which are going to have lots of weird symbols on them, and you should treat them as art. Right? They're not. I don't want you to try to understand them. I just want you to get a sense that there's all this stuff going on. I'm just going to say a few things whilst you're admiring the art. I'm just going to say a few things about why things are set up the way they are. So what we do is what we're going to do is describe how a process evolves. So a location, a resource, and a process. An action happens, and you get to a new location, a new resource, and a new process. Right? So what does that mean? If I'm standing here, drinking my cup of coffee, the action could be to walk along the corridor whilst drinking my cup of coffee, and then I'd get to a new location, which is the end of the corridor. I'd have less coffee in my mug. There'd probably be some coffee on the floor as well, and then I'd be able to decide to go to do a new thing, which would be to go off down to the other end of the building. So that would be an example of that kind of thing going on. Okay. Now, the thing is, we need to understand what is the structure of a complex action like. I just described something very complex to you. I described something with lots of things going on concurrently. I said, I'm walking down thing, but I'm also drinking a cup of coffee, I'm consuming resources, I'm spilling it on the floor, all that kind of stuff. And what I need to do, you just arrived in time for the artwork, Andrew. So we're having 2 slides of Greek artwork just to amuse people. So anyway, but the thing is, all that complex structure needs to be described, and I need to understand how it fits together. And the fitting together is the key thing. It's the compositionality. And the great thing that we've done in recent years in applying logic to program verification is to find ways of making things compositional. That means we can reason about big, complex things in terms of small, simple things, and have ways in putting them together so that the reasoning still holds good. Right? And that has been the massive win in recent years. That's why program verification that failed in in the later part of the 20th century, in the 70s and 80s, has suddenly started being a massive success because we got that compositionality thing right. Anyway, so what we're doing is we're describing the properties of this structure using things like this, which are inference rules from logic. And you say, if this thing is true, it holds, and if this thing is true, then this more complex thing is true. And that's what logic does. It takes simple structure and bolts it together to make more complex structure. Now, that might seem like a really trivial thing to say, but when you do that, there are lots and lots of mathematical properties you want of the way in which that structure, that composition happens, and we have to get that right. So this looks like it's some simple, pretty work of symbols, but actually there are lots and lots of really quite hard mathematical theorems we have to prove about this kind of thing. Okay, so one of the things we need, and this idea of bisimulation is probably really important. It says that when you have things like this, I described the walking down the corridor thing, it's possible that you want to know whether some other description of doing that is equivalent to it. And the notion of equivalence here in process is called simulation. It says I can simulate this by this under certain assumptions. But I want to know if these two things are equal, then not only does this one have to simulate this one, but this one has to simulate this one. We call that bisimulation. So if two processes can each simulate each other, then we have this notion of bisimulation. It's the notion of equality on process. And that is essential to setting up all the reasoning we want to do about it. So and there's a massive industry developed in this area, and it's very pretty, actually. So the second artwork of today, and this is going to be the last nasty slide, I promise you, is how we reason about all this logically. So we set up this weird and wonderful stuff in logic. The first line is the logic everybody learns in their Philosophy 101 class. The second line is Philosophy 102. The third line was brand new hot research 20 years ago. And the fourth line is kind of hot research kind of now. Right? So, but what we do is we say, if I've got a model of a system in terms of, I've forgotten about locations for the moment, just make it fewer symbols on the page. If I have some model of a system in terms of the resources and the processes that are going on, then I want to know what logical properties are true of that. So I write that as saying, this model makes these properties true. Now what we do is we expand, we understand how that works by breaking up this assertion of a complex thing, that this property and this property holds, into this property holding and this property holding. Now that's kind of the most trivial thing you can imagine in logic and, right? But the key thing is this one here. This different kind of and, we call it star. It says this system satisfies these two properties simultaneously if I can break up the resources, break up the processes into two things concurrently happening, and get this property holding of one bit of the system and this property holding of the other bit of the system. Now that is the big win. This operator star was the thing which made something called separation logic happen. Separation logic solved decades of open problems in program verification, basically. And it's now being used for real in places like Facebook to analyze their mobile code live in the production cycle. My colleague Peter O'Hearn at UCL is the person who drives that. And Peter and I developed this logic together at Queen Mary College some years ago. So it was kind of fun. Okay, so that's kind of the end of the scary stuff. I just want to make one remark. I made a bit of a fuss about equality a moment ago. So I said that two processes are equal if they can simulate one another, and that's really important. And the big important theorem when you're reasoning about these things is the following, that if two models of a system are equivalent logically, that is, they always satisfy the same logical properties, then they are equivalent as processes, and vice versa. And that's a very, very important theorem. It says that logical reasoning and process evolution, that is the evolution of models of distributed systems, coincide properly. And that means you can actually do the reasoning soundly and completely. Okay, so that's an important property. Let's move on. So if you're interested in this stuff at all, and I don't suppose you are, but if you are, there are some papers you could go away and read which tell the story pretty thoroughly, actually. You read them yet? No. Some of them, excellent. Okay, so the question is, how do we actually use all this weird mathematics? And I appreciate that for people here and perhaps watching that it is very weird mathematics compared to the kind of thing you're more familiar with. But just to reassure you, by the way, all we're doing is talking about dynamical systems, just in a different way. And we're doing it in a different way that allows us to deploy logical reasoning to understand it. That's what we're doing. But they're still just dynamical systems. There are translations between these sorts of models of systems and systems of differential equations that can be set up. It's just this way you get a direct relationship with logical reasoning, and that's useful. Okay, how do we actually build models then? Well, we build models in the way people always, I don't know what that exclamation mark is doing there. Oh, Windows has made a mess of my beautiful Macintosh slides. Okay, so ignore the exclamation marks and the hyphens. They've got nothing to do with me, honest. Right, so this is the way mathematicians always build models, or engineers build models. We start off and we make some observations about the world, and we do some kind of philosophical induction, and we end up with a mathematical model that makes some kind of sense. And then we ask ourselves, well, given that model, what would you expect to be true? What should happen? So we do some deduction and we get some consequences in the model of what we're building. And then we say, okay, how do we interpret those consequences back in the real world that we were trying to model? And that tells us whether or not we've got the model right or not. That's the validation process, insofar as validation means anything in modeling. That's a very interesting philosophical question, but this is where it happens. And we get to go around this cycle enough times until you decide that the real-world consequences of your model are close enough to what you can observe that it's a good model for your purpose. And then you quit and you get on and you use your model for what you intended it to do. Okay, so that's what happens. This is a somewhat non-trivial process. It's still more of an art than science. But some things are worth noting. The approach I described to you involving these abstract descriptions of process and resource and location are essentially scale-free. The actions I'm talking about could be my flicking of my finger or building a factory. They're still just actions. You might argue that the action of building a factory is something you'd want to analyse in a bit more detail, and that's what all the logical structure is for, to allow you to do that. But nevertheless, the theory applies whether it's a massive, great, big action of building a factory or just clicking the fingers. So, therefore, it's really important to choose your abstraction level very carefully. So you should choose the abstraction level. So what kinds of things are your basic actions? What are the basic properties you care about? Very carefully so as to answer the questions you want to answer. Now, if I want to answer questions about how much coffee I spill as I walk with my mug down the corridor, then the action should be about holding my mug and moving it around and stuff like that. On the other hand, if I only care about whether or not I get to the end of the corridor or not, I can probably forget about the coffee mug altogether. Right, it wouldn't be relevant to the model. So decide what the questions are, build the model accordingly. There are a number of ways of thinking about models like this. We have over the years done a great deal of work using simulations, Monte Carlo style simulations. So you've got this great big model which has lots of actions describing what's supposed to happen, and you just animate it by throwing some events at it, and actions start doing stuff, and you see what happens. And you can do a sensitivity analysis based on that. Just, how much does the behaviour of the model really depend on some of the choices I made, and stuff like that. And you can get some very pretty pictures of what's going on. You can also do something called model checking. Model checking is a technique for unpacking the logical properties that are supposed to hold of a complex system into properties that hold of simpler components of the system until you get to the point where you can decide whether they're true or not. So model checking is a way of reasoning, of automating logical reasoning about models. Also, when you're doing all of this, it's terribly important to remember Alfred Korzybinski's dictum that when you're building a model, it's not the thing you're modelling. The map is not the territory. So if you want a detailed description of everything that's going on, you may want to just look at the system itself rather than build a model of it, because whenever you build a model, you inherently make simplifications. But usually that's a good thing. Right? In practice, out there in the real world, and we deployed all this stuff, these ideas in a company called Hewlett-Packard for many years. It's important to remember that sometimes it's better to have a rather crude, not very well refined model now than a very beautiful, much more refined model in 6 months' time, because in 6 months' time it just may be useless. You may not, no need for it anymore. So there is a time value to modeling. Okay, so how are we doing? Here's an example of all this kind of stuff. Here's this is our security modeling example. Here the idea is you've got people who travel from their home via public transport or car to their office. When they get to their office, they go inside the building and they have to go into the lobby and they have to maybe use their badge to get in. And once if they have their badge, they can go through the way in and get to the interior office where they can do their work for the day. Moving documents around, whatever it is people do in offices these days. Okay, so now, so this is an example of 3 models being bolted together. They've got lots of locations, reception, lobbies, entryways. They've got lots of resources like badges and doorways and stuff in there. We've got processes. In this case, the processes will be people, for example, legitimate employees going from home all the way to their desks via all the bits of the model, or attackers trying to get inside the secure area by tailgating behind somebody when they go through the barrier with their badge. And then you have some security processes trying to stop that from happening. So here are three models being bolted together. The key thing in understanding whether this is correct or not is how these things fit together. We have an interface between this little model here and an interface between this model here. And the question is, how do we reason about those things? So what is the point of an interface? It mediates the composition of models. How do we talk about it? Well, we've got the models are all built on this analysis of distributed systems that I started out talking about in terms of location, resource, and process. What we need to do is to build, therefore, a notion of interface that uses those concepts. Allows us to talk about whether it's okay to bolt 2 things together, and if we do, what to expect of the composition. Okay, so we have to take account of the locations where the meeting of the models happens. We have to take account of the resources involved that are going to flow across the boundary between 2 things, and of the actions that make that happen. Worth noting that remember we talked about how you draw a boundary around the thing you care about, and the rest of the stuff is the environment that just throws events at you. Remember we started out talking about that? Well, when you start bolting models together, you're replacing a bit of that environment with a detailed model. Right, so that's what's going on. Okay. So here's what's going on with interfaces. You've got some model here with some locations and some connections and stuff going on. Another one here. You have an interface here. An interface is really therefore built out of 2 bits. It's the part of the interface that lives in this model and the part of the interface that lives in this model. And to specify an interface, you have to specify the locations that are involved, any constraints on the use of resources at those locations, and what actions are allowed to happen there. And provided those 2 things, for each of the things, are compatible, then we're good. We can make it work. Okay. So there's just one more thing we need to say about this. And this is something a little bit more abstract, a little bit more scary again. But this is something that's been terribly important in all the program verification work I described to you. It's called the frame rule. And don't worry about the details of the sim. I'm just putting it up there to entice you to go and find out more about it. But what it says is the following. It says, if I've got something true of a model, and some action occurs and I get to a new model, and something else is true, then I can do something clever. I can use the famous star operator I told you about to say, if I bolt on using an interface, this is an interface, I bolt on a new model, and there's some property that comes along with that new model, and if I do the same evolution to get to this other model here, with that same thing bolted onto it, then the new property I got to also is combined with that extra property that came from the new model. Now and there are some constraints on that. The new model has to have this property, indeed, which is kind of what I told you. And it also has to be the case that when A happens, it doesn't affect this model. Okay? So that's what we call a separation condition. And provided that separation condition holds, this rule, which is sound in the models I've been telling you about, logically sound, and that means it's supported correctly by the structure, provided that's true, I can reason locally about the structure of models. I can reason about this model, and this model, and this model, and bolt them together and get reasoning that works about the big complicated thing. And that kind of composition is precisely what we need to to reason about big complex distributed systems upon which everything we do depends. And the history is that worked for program verification, and we're going to make it work for big distributed systems. Thank you very much. More references there if you're interested. This is the more practical stuff.
Thank you for the talk. We have time for 5 minutes of questions.
Andrew.
So I'm wondering, with that compositionality thing that you just showed and the inheritance of properties when you augment the model, is that separation condition benign, or is that a sort of something to worry about? You know, when you, like the example you showed with the security situation with 3 different models bolted together, you know, what would it mean practically for the separation to hold?
Okay, it's certainly important, and getting that right when designing the interface, when considering what the right interface to consider between 2 models is very, very important. In practice, it's not problematic. In practice, it turns out that you can say, okay, there's a natural break between what happens in this model here and what happens in this model here, and almost all of the actions will have no effect on the other model that they're not part of, and you probably just end up isolating 1 or 2 key actions which do affect both things, and those are the ones you have to reason about carefully. So it's a way of managing that complexity. Yeah.
So if you assume a model for a distributed system, do you typically find that that's complete? Because my understanding is that once you set down a set of axioms, then it's either consistent or complete. And I mean,
so this is Gödel's incompleteness theorem. Yeah, it's the most misrepresented theorem in history. But it's so okay. So Gödel's incompleteness theorem does not apply to these logics because they're just not the kind of logic that applies to. It applies to a theories of arithmetic in first-order predicate logic, and that's what it applies to. The question, however, is a good one. The completeness question is a very good question. And the answer is it depends what you mean by the model and the completeness. And it depends on the level of abstraction. If I have chosen a certain set of things to care about, then I can most of the time ensure that I am going to reason completely about that set of things. But the model will often have much more detail in there that I'm not worrying about. And for the particular description I've used, it will not be complete for those things I didn't care about. I didn't model. So it's a question of you choose what to model, you set up a model of that, and if you do that well enough, you will get the kind of strong properties that you want. But there will always be things you didn't pay attention to and therefore aren't capturing. And also typically, if you were using these things for real, you'd find that there was some aspect of the model where you wanted a bit more detail, and then you'd have to extend the representation to handle that if you wanted to retain the strong properties you want. What you will always have is soundness.
Sorry, what was that?
What you will always have with these techniques is soundness, and that's often enough.
I'm a statistician, so I'm curious about the probabilistic models you use for your representations. I don't know if you can comment.
I don't understand that question, sorry.
In the beginning, you said you use you have probability representations of your systems. So I'm curious what sort of probability models you're using.
We're not using probability representations of the system.
Right.
We're using. Often we will employ probability distributions to describe the interface between a model and its environment. Not an interface between a model and another model, but between a model and its environment. So typically, imagine I have built a model of the post office. Right, so people will come in through the door and join the queue. So I'll just need to assume something about the rate at which they arrive.
So sort of queuing models, roughly.
Well, no, not necessarily. I'm just giving you an example of a queuing model. But I mean, it's quite typical to use queuing models. Yeah. Yeah.
I don't know if I could make another comment. So when you had a diagram at some point when you talked about model tuning, where you had, I think, observations, model, consequences to the real world. From a statistical perspective, it reminds the approximate Bayesian computation algorithm. Do you know if you've come across it? It's probably not related at all. But the idea is similar when you have some sort of prior model that you think, and then you simulate from that and compare some summary statistic, whatever you care about, to observations. Only keep the models that
But that's an
so
example of the mathematical
that's-
modelling process. I mean, the picture I drew, you could draw in page 2 of any book on applied mathematics, you know, with including probability theory. And in fact, I can give you a reference to a book on probability theory where you get something
Sure,
very similar.
I was just curious. It's a sort of sort of becoming fairly standard way of just formal fitting of automatic formal fitting of models. That's why I was wondering.
I think
if
that's a very
it's
interesting question.
related.
I think trying, from the philosophy of science perspective, of trying to understand the process of mathematical modelling, that is quite a new thing. I don't think, people haven't done it that much. I mean, in mathematics and physics, it's been, and engineering, it's been a kind of implicit notion that more or less for forever. And when you translate to these more logically oriented worlds, where the notion of model is a slightly more formal thing, and you want to understand the relationship between a logical model in a very formal mathematical sense and a model in the engineering sense of this is a good model of my bridge kind of thing. And the reason a lot of this stuff really works is you actually get a very convenient coincidence between those two notions of model. And it's the compositionality that's driving that, actually. And it's when you get this coincidence between the way in which you naturally write down the model as an engineer and applied mathematician and the way you'd formalize that as a logician, then you get all the naturality of the engineering model, but you get to bring to bear all this rigorous analysis of the logical methods. And that combination is somehow very powerful. It certainly seems to be the case that that's what's driving the success of separation logic and program verification, where the engineering model tends to be of computer memory in a very direct sense, and the logical model is the kind of thing I've been talking about. Yeah.
Okay, so let's thank the speaker once again.
Hey, thanks, guys.